Good day, everyone. We will end already our discussion covering now the last activity. That would be your activity 11. So this would cover already the last functional group for the final term, which involves already your ether. Now, the same as with the previous functional groups, we will mainly focus already on the physical and chemical properties of this functional group involved. In this case, that would be your ether. So regarding the nomenclature, since you already started that or you went over that under your lecture, we won't be going over that in this discussion. So for this particular discussion, the same as what we have been doing, now for the terms of use, again, taking any photographs or videos of any section of this presentation is strictly prohibited. The same is true. Some were sourced from Google and they belong already to their rightful owner. It is basically, so those photographs are basically used for educational purposes only. Now, to introduce already your ether, so based already on your lecture discussion, this is again one of the hydrocarbon derivatives, and for some references, they will describe ether to be a derivative of water, considering that again, for your water, we have two hydrogen atoms, and looking at the structure already of ether, instead of hydrogen atoms, we will mainly be looking at a carbon-containing alkyl or aryl group. So what bridges already this two carbon containing group would be a central oxygen molecule containing already two pairs of electron. So in this case, again, let us try to consider now specifically the physical and chemical properties of ether. So basically, since it looks like water, some properties already of water will have to be observed in your ether, especially its shape. That is a bent shape. Since water is bent, your ether is also bent. But regarding already the intramolecular forces of attraction, specifically the ability of your water to form already hydrogen bond with itself, your ether cannot do hydrogen bonding, considering that again, what we will be observing here would be a bond between your oxygen and carbon as opposed to an oxygen and hydrogen. But again, your ether can again form a hydrogen bond with other molecules. That would be your intermolecular forces of attraction, but not the intramolecular forces of attraction, your hydrogen bond with itself. Again. So next would be for your physical and chemical properties, starting with the physical properties, let us try to consider already the general representation. That is again your RO, R prime, and your R and your R prime will designate already any carbon containing group, whether that is an alkyl or an aryl group. As for the polarity, ethers are considered to be polar due to their bent structure, but more specifically, since they contain already your central oxygen atom, which creates a dipole moment, which we were able to discuss previously. So we won't be going over again every principle that we will be encountering, since we were able to discuss that during our previous discussions covering already the other functional groups involved. Next would be for the boiling point, it will have already lower boiling point compared to an isomeric alcohol. So if you're talking about isomeric, these are compounds with the same formula but a different hydroxyl group, since your alcohols will contain already or will be represented by your ROH prime. So they will have a lower boiling point, considering that your ethers, as what has been mentioned a while ago, cannot form intermolecular hydrogen bonds with themselves. However, for alcohols, they can. So that is for your ether versus your alcohol. Because again, going back, if we will have to compare already the bonding of your alcohol and your ether, for your alcohol, that's oxygen to hydrogen, meaning since it contains already your O2H, that is a strong intermolecular forces of attraction, it would require higher energy to again destroy the bond present between your oxygen to hydrogen. As opposed to your oxygen to carbon, the energy needed here is again weaker as opposed to your oxygen to hydrogen, as what is observed in your alcohol. Thus, the lower boiling point as opposed already to their isomeric alcohol. Now, for the solubility, regarding again solubility, we need to consider now the occurrence already of the CC bond, because generally for lower members they are still miscible or soluble in water, considering that again they have your central oxygen atom which can form hydrogen bond with water but not with other ether. So again, to clarify that, with water but not with other ether. Now, regarding solubility, as what has been mentioned a while ago, if the R group or the R prime group will have longer CC bond, then ultimately this will lead to a decrease in terms of their water miscibility or solubility. Next would be for the flammability. So for your ethers, they are recognized to be a flash fire hazard, meaning they are highly flammable. Now for the reactivity, they usually react already with oxygen to form what we call as your peroxides, which we will be presenting later on under the specific chemical reactions to which your ether will have to undergo. So proceeding with that specific part of our discussion for the primary chemical reactions, let us try to consider already three chemical reactions. Now, ethers are generally considered to be inert. However, regarding already their reactivity, depending on the compound involved, whether that is an acid or even a base, we need to present now how your ethers will have to react. Starting, of course, with the most characteristic reaction of your ethers, your strong acid cleavage. So if we are talking about cleavage, if your ethers are cleaved or specific atom is cleaved, it means that they are isolated, they are broken. Now, usually this involves already a catalyst in the form of heat or chemicals such as your strong acids and your strong bases. Now, in principle, the reaction is a nucleophilic substitution reaction. So we won't be going over this since we are done with that during our previous discussion. You might want to revisit them if you were able to forget already the principle covering now certain chemical reactions. Now, since we are talking about nucleophilic substitution, that can either be your first or second SN1 or your SN2 type nucleophilic substitution, initiated primarily by protonation. Again, we've been talking about protonation, ation, addition of proton. So mainly, this will be coming from your hydrogen atom that is actually part of your acid. So as what is presented here in the general equation, suppose we have already your ether reacting with, in this case, a strong acid. Recall, what are your strong acid forming groups? That would be your group 7A, your halogens. Once they react already with your hydrogen, they form already your strong acids, your hydrofluoric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid, etc. Your for chlorine and bromine, I attended. So depending already on your again mnemonics, again, try not to forget already your elemental groupings. So for the mechanisms as to how strong acid cleavage will have to be observed in your ether, it starts with your oxygen atom being protonated. So if we have already, let's try to consider already a specific ether. Let's say they are unsymmetrical. So you have your central oxygen. Let's consider already your methyl. Let's consider already your ethyl. So this is basically your methyl, ethyl, ether or your methoxyethane. So depending already whether that's your IUPAC or your common name, again, try to remember how you name already your compounds. So since we have already your reacting hydrobromic acid, since it involves protonation, the hydrogen here will protonate already the central oxygen, resulting already in the formation of what we call as your oxonium ion. So if you're talking about oxonium ion, this occurs as a product of protonation of your central oxygen, allowing already your oxygen to have a positive charge, meaning there is already an excess electron. So it is willing to donate already that electron. So after the formation already of the oxonium ion, this will have to be attacked already by the halogen. Since your halogen is electrophilic in nature, we will have to describe it as being electrophile or nucleophile. Since it contains already more electrons, basically, your halide ion is, again, a nucleophilic ion. It contains more electrons as opposed already to your oxygen. So when this happens, it will start to form already what we call as your alkyl halide. In this case, since we utilize already your hydrobromic acid, it will form your alkyl bromide. So what will happen here is that after alkyl bromide is formed, alkyl, since we utilize already your methoxyethane, it can form already what we call as your methoxy, again, halide here is your bromide. So if we will have to consider now the formation of your methyl bromide, again, this is already your methyl bromide from your methoxyethane. Since it involves protonation, the hydrogen has been bonded to your oxygen to form your OH functional group. Your bromine can bind already to your R group, forming your alkyl halide, specifically as what has been presented here, your methyl bromide. Now, if the temperature is high, suppose we have the incorporation already of another catalyst, the alcohol can further be protonated, your OH functional group can further be protonated and react with another halide. So we already have the formation of your alcohol. So once we have another molecule of your hydrobromic acid, your hydrogen will combine already since it involves protonation. This will form already your water. What's left is your bromine will then combine with the remaining alkyl group to form already a second compound which involves already two carbon atoms, your ethyl bromide. So that is already your acid cleavage. So basically, the product here would be the formation of an alkyl halide. Whether that's just one alkyl halide or two alkyl halides, it will depend already on the concentration of the acid. In this case, that would be your hydrobromic acid. But then again, we can use another strong acid in the case of your hydrochloric acid to form your methyl chloride and your ethyl chloride. If you use your hydroiodic acid, you'll be forming methyl iodide and your ethyl iodide. So that's your strong acid cleavage. Next would be your auto-oxidation, or as what has been written a while ago, this will involve already the formation of your reactive peroxide. That's why auto-oxidation is also known as your peroxide formation. So what is involved here is again the formation of your highly reactive peroxides or your hydroperoxides. And this will follow already a specific pathway that is again the formation of a free radical because your hydroperoxides and your peroxides are considered to be free radicals. And the main characteristic of free radicals is that they are highly charge. So they possess already a specific charge, negative to be precise or to be accurate, that will cause now the obstruction of other electrons from the surrounding cells if we are talking about again your radicals inside the body or other compounds if you're talking about chemical reactivity. So in principle, your ethers will have to, since it is oxidation, they will have to react already with oxygen to again produce your radicals. Now, in this specific chemical reaction, there is actually a condition. So the auto-oxidation or the peroxide formation is catalyzed already by light or another catalyst. The more common catalyst is already your heat. And it occurs when ethers are stored for a long period of time, as in any compound. That's why if you will have to consider, as simple as vitamin C, your vitamin C on prolonged exposure, and if we will have to expose that to light, it will undergo what we call as your auto-oxidation. So let us try to present already an example. Let's say, for example, we have here again your ether. Again, this is unsymmetrical. Let's say, for example, the R prime here again is your methyl, and we have again your ethyl. So that's your methoxyethane undergoing oxidation to form already. Notice what is formed here would be OOH. So this is actually a derivative of an acid. So if we will have to consider now the oxidation already of your ether, it is possible to form already the corresponding acid. So we will just substitute already your R prime with your CH3 and your R with your CH3 since we utilize already an unsymmetrical ether compound. Now, because your peroxides are extremely sensitive already to heat, they must be tested for and removed before distilling in the actual laboratory. So if this will not be observed, they will lead already to certain explosions. Because again, your peroxides are highly reactive. So consideration in, again, observing already auto-oxidation procedures in the laboratory, we need to properly monitor already heat. And apart from heat, even a simple vibration or a shock, this can also cause already explosion of your ether. again, under auto-oxidation. So that is specifically if we are distilling of your ether. So next would be your electrophilic aromatic substitution. Since we have the word aromatic, this is specific already to your phenyl-containing ethers. Now, the R group, in this case, we have your methyl, and the other R group here is already a phenyl. Phenyl group. So under your electrophilic aromatic substitution, let us try to consider already an example. Suppose we have already from your lecture discussion, suppose we have already your anisole base. They will readily undergo what we call as your electrophilic aromatic substitution. So specifically, under this type of chemical reaction, the ether oxygens lone pair will have to donate already the electron density into the ring. So if this will happen, this will allow already your halides to again bond to your phenyl group. So as a result, the OR group is a strong activating group, and this is where you will be observing already what we call as your ortho, meta, or your para position. But then again, if you're not able to encounter this in your lecture or a separate discussion discussion is yet to be presented in class, let us try to introduce already your ortho-meta para position. For your ortho position, this will pertain already or describe your alkyl groups that are adjacent with one another. If we are talking about your meta position, we have already one carbon atom in between two alkyl groups. But if we are talking about your para position, the two alkyl groups are found already in the opposite of each other. So that's your ortho meta para that is applicable already to your aromatic compound or your benzene based compound. So going back with our discussion, if you would have to consider now your electrophilic aromatic substitution, suppose we have already your again compound, but ayaw magsulat. Suppose you already have so allow me to pick this first. Suppose you already have your compound reacting already with your bromine under specific condition. This time, our catalyst involved here would be your acetic acid, two carbon-containing acid. What will happen here would be the formation already of your two compounds that can either have your ortho or para position. So ortho again is they are adjacent with one another. Para, notice that again, the positioning of the bromine is again in the opposite side of your methoxy part of your ether. So this is again your electrophilic aromatic substitution. Basically, what happened here is that the aromatic ring becomes more reactive towards your electrophiles. And electrophiles, since they are electron poor, they will be again attracted already they will be attracted already to a nucleophile. In this case, your nucleophile would be your, again, aromatic ring since it contains more electrons. So again, as what has been presented a while ago, your aromatic ring, since it is a nucleophile, it is more reactive towards your electrophiles or you're represented as your E positive. And apart from that, let us try to, we also have one pala. I also included your epoxide formation, but this is specific to from the word epoxide. Epoxide is applicable already to a three-membered cyclic ring. So this is an example of an epoxide. So regarding epoxide formation or your cyclic ethers, for your cyclic ethers, they are highly strained, meaning, again, strained in a way that if you would have to evaluate now how the atoms are involved or attached already to the carbon atoms, they are chemically reactive, which serves as an intermediate in producing or synthesizing another compounds. Regarding how they are formed, let us try to consider now an alkene. It always starts already with your unsaturated hydrocarbon. So if we have an alkene and we have your peroxy acid as what has been presented a while ago, under your auto-oxidation, the formation of your peroxides, we will be forming already your epoxide. So the central oxygen will be coming from your peroxide or your peroxy acid, and of course the carbon atoms, the other carbon atoms will be coming from your alkene. Now, apart from this, since we are talking about your epoxide formation, the primary product involved here would be, again, as what is being presented a while ago, that would be your epoxide. But as a secondary product, we will be recovering already the original acid. In this case, if we have already your acetic acid, if it contains two carbon atoms, then what will be recovered under epoxide formation would be a two carbon containing acid. So that is under your epoxide formation. So apart from this, it is possible, apart from your straight chain alkene, it is possible for your cyclic alkene to be used as, again, a base compound to produce already an epoxide. So in this case, we will be forming what we call as your epoxy cyclohexane. Notice that again, the double bond or the unsaturation will have to be reduced along with the recovery already of this specific acid used in that chemical reaction. So that would be for your epoxide formation. Now, apart from the formation or recovery of epoxide, let us try to consider now how would your epoxides undergo chemical reaction, since we already have the presentation of some chemical reactions here. So if your epoxide will undergo already basification or reaction already with a strong base, in this case, your sodium hydroxide, we will be observing already the opening of the epoxide moiety. Notice that again, this is a cyclic structure, but upon adding already a strong catalyst, this time your sodium hydroxide, we will be observing already the formation of an alcohol, and instead of a cyclic structure, it becomes linear already. So it is called vicinal diol because from the word vicinal, the diol or the all functional group, your OH functional group, will be located at the terminal ends. That's why we have the attachment of the word vicinal. So the same is true with a cyclic epoxide. This will cause the epoxide part to open, forming already your OH functional group. So where will your OH come from? It will come from, again, your sodium hydroxide, since it will give already your hydroxyl functional group. So that's for the epoxide formation. Let us try to go over the preparation already of ether. So for the preparation of ether, they are commonly prepared from your alcohols. That's why for the primary preparation, it involves what we call as your acid catalyzed dehydration. So for the acid catalyzed dehydration of alcohols, this is specific already to your ethers that are symmetrical in nature, meaning the left side and the right side will have to be the same. So we will be recovering diethyl ether, dimethyl ether, or your methoxymethane, ethoxyethane. Now, for the unsymmetrical ethers, that is where we will be observing already your Williamson ether synthesis. But before we proceed with that, let us try to go over first your acid catalyzed dehydration. So since we've mentioned about a while ago regarding now the use of your alcohol, suppose we have two alcohols here. Let's say, for example, we are using already your methanol plus another molecule of your methanol in the presence already acid catalyzed. So in the presence already of a strong acid, since it causes dehydration, what would be the common dehydrating agent, which is a strong acid? That would be your sulfuric acid. So in the presence already of your sulfuric acid, it is possible for us to recover already your dimethyl ether. So where did the CH3 came from? It came from your methanol. The other CH3 came from your methanol. Since this is dehydration, your OH will combine already with the hydrogen present in your sulfuric acid. Since it involves two molecules of alcohol and we have two hydrogen atoms, each hydroxyl functional group will be receiving hydrogen atom to form as well two molecules of water for each of this reaction. So that's your acid catalyzed dehydration. So next would be, if we will have to consider, apart from apart from sulfuric acid, let us try to consider now heat. Because not all the time we will be using already your acid catalyzed dehydration. Now, regarding the role of temperature, if we will just observe already heat, since heat is a catalyst, this will lead already to the formation of, again, as what has been presented a while ago, your oxonium ion. So the alcohol, as represented again, ayaw na naman magsulat, as represented already by your ROH, is protonated already to form your oxonium ion. So since this is protonated, since it already contains your hydrogen, this will lead to the formation already of your RO positive, gaining already a positive charge due to protonation and two molecules already of hydrogen. Now, a second molecule of alcohol will attack already the carbon of the protonated alcohol. So suppose we have already your methanol originally presented here. So if our sample here is your methanol, allow me to erase your R and specifically substitute already a methyl group here. So after protonation, since we have already your CH3 and we have already the oxonium ion, a second molecule of your methanol, your CH3OH, will have to attack now the carbon atom that is present in your protonated alcohol. This will cause already the displacement of your water molecule, H2O, H sub 2 oxygen. So what will happen with your CH3? Ultimately, it will have to be liberated. So since your water molecules from the protonated oxygen will form already your water, what is left here would be your methyl group. So the final ether will be formed after your second alcohol will undergo deprotonation, meaning this hydrogen will have to be removed, allowing already your methyl group from the first alcohol molecule to attach itself, forming already your dimethyl ether. So that is again with the application of heat rather than your acid catalyzed dehydration. So next would be your Williamson ether synthesis. Now, if we are talking about your Williamson ether synthesis, if the other one is for symmetrical ether, your Williamson ether synthesis is for unsymmetrical ethers. Although symmetrical ether is still possible. But let us try to consider again both of them, whether it's symmetrical or asymmetrical. Let's try to consider now the principle behind your Williamson ether synthesis. So this is described to be as the most versatile method in preparing both your symmetrical and your unsymmetrical ether. So the principle relies already on your nucleophilic substitution reaction, specifically your SN2 reaction. So if we will have to consider an alkoxide, sodium alkoxide. Alkoxide, this is an ether to which the other R group has been removed. And substituting that R group with a specific element, in this case, you have your sodium. Because again, originally, we have already your ether represented as your ROR. But if you will have to remove one of these alkyl groups, it becomes an oxide compound. So the reaction will have to proceed if we have already the formed alkoxide. In this example, we have your sodium alkoxide. What will happen here is that again, it will have to substitute already. Suppose we have already the presence of your alkyl halide. Again, alkyl halide as represented by R, halide as represented by chlorine. Now, the alcohol is the first, again, as what is being presented here. Before we form already your alkoxide, we have already your alcohol. So suppose we have already your alcohol. Now, the alcohol will be treated already first with a strong base. In this case, since they use already sodium, let us consider now your sodium hydroxide. This will lead already to the formation of your sodium alkoxide. So how did the treatment of alcohol proceeded? Let us try to consider, suppose we have already your ethanol as represented by your CH2, CH3OH plus your sodium hydroxide. Your OH and your hydrogen will be abstracted to form already again your ever compound water. What will happen since your oxygen is charged already and your sodium is positively charged, your sodium ion will combine already with your O part to form already your sodium alkoxide. In this case, that's your sodium ethoxide, S, because we have two carbon atoms. Again, from your lecture discussion. So after the alcohol forms already your alkoxide ion, the alkoxide will react already with a primary alkyl halide. Silent H. Now we have your primary alkyl halide as what has been presented a while ago, alkyl halide, depending again on the number of carbon atoms that as presented generically as your alkyl halide. So what will happen here is that again, since we have the R group from your alkyl halide, what will happen here is that the R group will have to substitute already your sodium, forming now your ether. Since our halide here is your chlorine and our positively charged ion here is your sodium, they will have to combine to form already your sodium chloride. So we will be observing already a substitution reaction here. So that is already your Williamson ether synthesis. So when does it become unsymmetrical? Suppose the alcohol used is ethanol and the halide formed here or the halide alkyl halide used here is your methyl chloride. Your methyl chloride, it is possible to form your methyl ethyl ether or your methoxy ethane. That makes it already unsymmetrical. But if the alcohol used is methanol and the alkyl halide used is methyl chloride, since the R groups are methyl just the same, they will form already a symmetrical ether, your dimethyl ether or your methoxy methane. So the same is true with the other compounds presented here as your ethoxide and your methoxide. So that is for the preparation of ether, either again your acid catalyzed dehydration or your Williamson ether synthesis. So what we have here involves already your sample ether compounds. So they can either be alkyl or your aryl. Your R groups can either be your alkyl or aryl. Let's say, for example, they can also be symmetrical or unsymmetrical. Symmetrical compound, dividing already your compound left and right, you'll notice we have the same alkyl groups, making it symmetrical. Thus, the name is your diisopropyl ether. Iso, considering that they formed already your fishtail on both sides. Next, we have also your cyclic ring structure, but they are unsymmetrical. Since they are cyclic, we use your cyclo prefix. So we start by naming already the one with again, the one that is lesser in terms of the number of carbon atoms, 5. So that's your cyclo. 5 is spent. And since that is the shorter chain, we attach your suffix oxy. So cyclopentoxy, cyclohexane. So that's already your ether number 2. But then again, we won't be going over your IUPAC name because that is part already of your lecture. But just to present already some examples of your ether compounds, we have the following. Notice again the usage of your prefixes tert and iso to denote already positions of your alkyl groups, whether they form already your again cross or your fishtail. Utilize already the correct prefix, that would be your tert and iso respectively. Next would be you have here already what we call as your cyclic ethers. So as long as you see already this again configurations, they are already they have already their parent name. So you have your ethylene oxide, you have your THF or your tetrahydrofuran, your furan ring, your pyran ring. So if you encounter those words, furan, pyran, they will pertain already to this specific, again, structure. So moving on with the activity, as presented already in your manual, you have what we call as your salting out of ether. So we have again your separatory funnel. Suppose we will have to add already your ether and we will have to add already your water. Since they possess already different polarity, ultimately you will be observing already a heterogeneous mixture. However, if we will have to increase now the concentration of water, it is possible already for your ether to again undergo miscibility. Suppose these triangles will represent already your ether, and we have already your water. What will actually happen is that your water will form what we call as your solvation shell. Solvation shell meaning they will have to form again an enclosure in your ether molecules. So again, allow me to draw first your water. So again, this is your water, your HOH, your HOH, your HOH, your HOH, your HOH, your HOH. Since we are observing already your molecules, they are capable again of O2H, that's your hydrogen bond. So what will be happening here again, as what has been mentioned a while ago, is that they will form already your solvation shell. Your solvation shell will allow already your ether to be enclosed, allowing now the formation of your hydrogen bond. Because in your ether, it still contains your central oxygen atom, allowing it to form hydrogen bond intermolecularly. Because if you're talking about molecular hydrogen bond, it is not possible for your ether. So if we will have to, as what has been presented a while ago, increase now the concentration already of water, we are promoting already the water solubility. Again, ayaw na naman mag-write. We are promoting again the water solubility of ether. That's why it is possible again for ether to form a homogeneous solution with water if we increase now the volume of water. Now, the principle of salting out is that after forming already a homogeneous mixture of your ether and your water, let us try to recover already the ether component. How is that possible? Again, we utilize already what we call as your sodium chloride. So again, if we will have already the incorporation of your NaCl or a highly water-soluble inorganic salt in the form already of your sodium chloride, recall sodium will contain your positive, sodium chloride will contain your negative ions, your sodium and your chlorine ions, respectively, as positive and negative. So, as what has been mentioned a while ago, once there's already a hydration shell and once we incorporate already your NaCl, what will happen here is that when a large number already of sodium chloride is added in our solution, the highly charged sodium ion and your chloride ion will strongly attract already the surrounding molecules or the water molecules that already formed now what we call as your solvation shell. So basically, they will compete already for the binding of water. So if your NaCl will already bind to your water molecules, this will allow already your ethers as represented already by triangles to escape already the mixture forming already a two layers. One, that of your ether, and the other would be the aqueous NaCl already. Considering that again, your chlorine ions, we have already the presence of your chlorine ion there. They will be able to compete already for the surrounding water molecules. So as you increase now the concentration of sodium chloride, this will draw already more water away from your triangles or your ether. So this will result in the effective reduction already of free water available to dissolve already your ether. As a result, as what has been mentioned a while ago, your ether will separate already from the mixture to form another layer, considering that it has formed already your aqueous sodium chloride solution. Now, this will be distinct considering that if we will have to evaluate already your separatory funnel later on, you will notice the formation already of two layers. One would contain already your aqueous sodium chloride and the other would be your ether component. So that is now the principle behind your salting out, meaning we will just have to incorporate an ion that is capable of removing already your water, allowing now your triangle ethers to move out of the mixture. So that's again your salting out. Next would be for the pharmaceutical uses or relevance already of ether, the same as what we've been discussing already for the previous functional groups, they too will again be found in your pharmaceutical compounds. Now, conventionally, your ether, as what is being presented initially, is being utilized as an anesthetic in your lecture as an anesthetic. However, since your ether compounds are susceptible already to presenting significant toxicological effects, they are no longer used in the modern healthcare system. So for your diethyl ether, it is again historically used as a general anesthetic. But since it presents significant toxicity, it's no longer used as your diethyl ether. So in order to reduce now the occurrence of side effect or toxicities, what they use already is that they substituted now your hydrogen atoms with a halogen. This substitution led already to the development of a or a safer alternative for your ether in the form of several general anesthetics that contain already your halogen. So we are still looking at your ether functional group, but instead of the conventional hydrogen atoms attached to your carbon, this time we have the attachment of your fluorine. In the case of your sevoflurane, this is safer as opposed to your diethyl ether, and in terms of its activity, it's actually longer in terms of how it presents its biological activity. That's your general anesthetic property. Now, apart from this, let us consider already another example. So for your omeprazole, if we will have to identify now the ether component of your omeprazole, we'll be looking at this part. You have your methyl, and of course, you have already the other side chains. You also have your methyl, and you have as well the side chain. So for your omeprazole, this is classified as a PPI, your proton pump inhibitor. It reduces already the production of stomach acid. So it is used already to treat your heartburn. Apart from your heartburn, we have a condition known as your GERD, or your gastroesophageal reflux disease. And of course, to prevent already ulcers, mainly attributed already to excessive production of gastric fluid, or that is your hydrochloric acid in our stomach. Next would be tramadol. As for your tramadol, this is already your ether part. So regarding already your tramadol, notice we have the attachment already of your phenyl. That's why if you will have to consider now your tramadol, it is a derivative of your phenyl propylamine. Amine because we have again your NCH3, meaning all hydrogen atoms were already substituted. Now, for your tramadol, this is classified already as an opioid analgesic. Being an analgesic, it is used again to treat now pain. Apart from pain, more primarily pain. So being an analgesic, it is used already to treat pain. But regarding the type of pain, it is used to again manage moderate to severe types of pain. That is why if a patient is no longer responding to the usual paracetamol, ibuprofen, your celecoxibs, your mefenamides, they are usually prescribed already with a higher level of analgesic, your tramadol. But this is a controlled material, that's why it needs already a license before your tramadol is prescribed and dispensed to the patient. Apart from this is your codeine. Excuse me. Your codeine. So we have your ether functional group. So this is also the same as with your tramadol. This is also an opioid analgesic, mainly used again to treat your moderate to severe pain. Now, apart from that, your codeine is conventionally used as a cough suppressant, or what we call as your antitussives. So for your antitussive, another example here may be what is common is your dextromethorphan, your Formula 44 ng Vicks. So antitussives, they directly act already in the CNS to suppress now the cough reflex. But antitussives are used already specifically for dry cough, because if you will have to use already antitussives in your productive cough, you won't be able to excrete already the mucus present already in your respiratory tract. So this is again specific to your dry cough. Next would be Wala na pala. You can actually search for another compounds that contain already specific functional groups. But as what has been presented previously, we have several functional groups that can be found already in a single pharmaceutical product. Regarding the relevance, you will be talking about that under your organic medicinal, because each functional group will be responsible for a characteristic activity that enhances already how a drug will work. Let's say, for example, some of them will enhance already solubility, some of them will enhance already binding of the drug to a specific receptor in order to again enhance the overall activity of certain medications. So if you are trying to design a drug, you actually modify now certain functional groups in order to optimize now the activity of those medications. But then again, you will be talking about that under your organic medicinal. So see you during your second year level. So that is what we will be talking about your org med, and that's actually fun as opposed to your chemistry, your basic chemistry, because we will be understanding already how certain medications work, and you will be evaluating how they will affect already a specific receptor, a specific cell, protein, etc. So that ends our discussion covering already your ether, and this will be part of your last quiz along already with the posted supplementary material covering your stoichiometry. So reminder regarding stoichiometry, the document actually is a standalone file. So as long as you follow already the procedures there, you will be able to understand now your stoichiometry. What is important for you is to go over already, your uh, is to go over already your, what do you call it? Naglalag tayo. Your balance chemical equation. So allow me already to share now the file. Let us try to have a short recall regarding your stoichiometry, because this is actually part of your high school, if I'm not mistaken. So for your stoichiometry, what is important here is for you to be able to present now the chemical equation correctly. Apart from correctly presenting now your chemical equations, what is more important is to balance. Ay, ang laki naman. Is for you to balance, already your reactants and your product, because the number of moles will already affect the computed number of reacting moles specific already to your reactants or specific already to your products developed. Now, if we will have to consider now the presented, I'm still finding out how this works. Ayaw niyang masulatan. If we will have to consider now the specific reactants under activity 13, we have already what we call as your salicylic acid and your acetic anhydride. Now, what is important here is for us to be able to again present their correct molecular formula, because the molecular formula presenting already your compounds in their molecular formula allows us to properly visualize already your compound production or the product production. So in this case, but ayaw mo, wait lang. 2 minutes. In this case, if we will have, hala, ayaw niyang masulatan. If we will have, highlight naman yun. If we will have to reconsider, okay. If we will have to Ching. Ay, pareho sila. Okay, nonetheless, let us try to go over already to save time. After presenting already the reactant and the products in their molecular formula, I included now the structural formula for each of these chemical species for an easier tracking on how your products were able to be formed. Now, since we have already your acetic anhydride and your salicylic acid, let us try to consider presenting them and identifying the volume as well as the weights used. So just follow already what has been presented in the file. So you need to present them in their molecular formula and the correct volume or weight in that specific experiment. So after presenting now the chemical equation, try to balance them already. Balance now the number of moles of each atoms involved in your reactant and in your product side. So once you were able to balance them, try to go over already the computation in determining now the molecular weight. Since you have your molecular formula, you will be needing already the atomic weight of each of the elements involved, your carbon, hydrogen, and your oxygen. We are not rounding them because based already on our preliminary discussion, rounding already the atomic weights will change already the ratio of the subatomic particles involved. That's why we need to settle already with the actual molecular weight as presented already in the periodic table. So commonly for oxygen, that is being rounded to 16, but no, we settle with 15.999 to accurately represent already the ratio between your electron, your neutron, and your proton. So after computing now for the molecular weight of each of the chemical species involved, try to determine now what we call as the number of moles. So for the number of moles, that is a ratio based already on the balanced chemical reaction with the computed molecular weight. So again, follow through with what has been presented here. You will be able to arrive already at the correct computation for the number of moles, because number of moles is significant or relevant considering that we need to understand which of them is your limiting reactant. So from the word limiting, it limits already the reaction. So once the limiting reactant is already exhausted, we won't be able to form another or any more products. Now, next is after computing for the number of moles, we will be able to compute now for what we call as your theoretical yield. Now, for the theoretical yield, from the word theoretical, this is supposed to be the actual weight of the aspirin that we will be recovering based already on the balanced chemical equation and, of course, the computed number of moles for your number of moles and relative to the molecular weight of your aspirin on your salicylic acid. So after that is to again plot them already after computing now the theoretical yield, plot that already with our working equation for the percentage yield. And that is the ratio between your actual and your theoretical yield multiplied by 100, considering that we are again talking about percentage yield. So after computing now the percentage yield, let us try to again read the value. So you were able to recover 43.70% or arrive at a value 43.70%. So what would be the implication of 43.70%? So that is the percentage yield, or based already on the actual weight of 0.57, supposedly you were able to recover a weight of 0.57 grams of aspirin. Your percentage yield is just 43.70%. So we need to account now for other factors that have contributed already to a low recovery of your aspirin. So other factors during the activity, even though you did not perform that, let us try to understand what are the variables that could potentially affect now the recovery of aspirin. So the procedure involves filtration. So other compounds might have been left already on your filter paper, which could precipitate out as aspirin, leading already to a reduction or to a low percentage yield. Apart from that would be the strict adherence already to temperature, because we need to monitor or we need to strictly observe now increase or decrease in terms of the temperature of the solution, because reducing the temperature and increasing the temperature affects now the solubility of your compound. So if you will not be able to observe strict temperature regulation, it too will affect already the percentage yield. So we will be going back already with the previous laboratory considerations made in the classroom along with your lecture discussion covering already your unit 1. So please do not forget already to analyze now the values that you will be computing later on. So if you'll have to review now the material posted in the Google Classroom, try to evaluate now the values. Try to read them. What does the 2.16 grams of acetic acid imply? What does it indicate? What does the 0.02 moles of acetic anhydride imply? Again, try to recognize already the values and relate that already with the procedure. So if you will have to increase now the volume of acetic anhydride, will you be able to recover more aspirin? Conversely, if you will use more salicylic acid, will you be able to recover more aspirin if you will have to reduce or increase the volume of acetic anhydride? Again, try to provide relationships as what we have been doing for the previous discussions. So that ends already your short presentation for your stoichiometry because actually, the file, how I presented already your stoichiometry, that's the easiest process I can think of. Because if you will try to read already the stoichiometry procedure in some of your reference books, ultimately you will encounter technical, uh, what do you call it? Naglalag na naman tayo. Your technical terminologies. Now, try to do it on your own. Try to substitute already the values involved and then recompute now the recovery from those specific values. So, try to assign weight and volume for your salicylic acid and your acetic anhydride and determine already the theoretical yield and the percentage yield corresponding already to the weight and volume assigned for each of these chemical species. So the coverage of your next quiz would be your ether and your stoichiometry. So that will conclude already your final term activities or assessments.